Good afternoon, all. Uh, these videos are for solving the numericals, the methodology for that, right? Some of the students suggested me if I'll give you these videos, then it will be easy for them to solve the numericals. So for all the four topics, yes, I'm going to do this, right? And second thing is, now I'm starting with time domain analysis. In that, four things are there in time domain analysis. One is static error coefficient, second one is your underdamped performance numericals of that second order system, third one is Rouse stability criteria, and fourth one is root locus. So one by one, for each topic one video. In this way um, we are going to solve the numericals, right? I'll just show you the methodology for solving one example, the formulas that you should remember, and how you are going to solve numerical, the method for that, right? So one numerical I'll take, rest of the things, many of the numericals we have already done, so you go through it. um, yeah, so I'm talking about now second topic, and that is time domain analysis. And for that, under this topic, the first subtopic that comes is your steady state error. So for that, we'll see what are the formulae and how you are going to go for it. So I'm talking about A now, and that is steady state error. The formulas that you are going to remember for, I'll write formally. Number one, all the standard test signals, we used to say. Many a times you'll find, yes, small short answer questions are also asked based on this. Number one, step input, I'll write unit step input. And how you are going to represent it, 1 by s in Laplace domain. Alright, second one is your unit ramp. One by s square. Unit parabolic. One by s cube. And third one is unit impulse. And it is 1. Okay, so you are supposed to remember 1 by s, 1 by square, 1 by s cube. In short, if you want to draw the this thing waveform, otherwise I'll just draw it freehand. Let me right, so just a step, a ramp, parabolic, and impulse. Okay, then the second formula is E of s, how to get the error in s domain, and the formula is R of s upon one SR of s. SR of s upon 1 plus sorry, that is for error, right? Wait. This is errors. For steady state error, you'll find 1s is coming over here. So just E, it is R of s, 1 plus G of s, H of s. Then the next formula is for steady state error, ESS of t. that is limit s tending to 0 s r of s after applying the final value theorem. Now how we got these things already is there in the notes, right? I'm just writing all the formulas that you are going to require for solving the numericals. So our main intention is to solve numerical. Yeah, third one. Then fourth one will be all the static error coefficients. So all means three you are aware of. So I'm writing first one, that is KP, position error coefficient, right? Many a times question comes, you calculate these coefficients, G of s, H of s. Okay, and in that case ESS of t formula is A upon A means whatever is the amplitude of your signals, the input signal that is there. If it is unit, it will be 1. If it is not unit, then some A will be there. So that A I am writing it over here. 1 plus Kp. Then Kv, that is limit s tending to 0 s G of s H of s. And in that case ESS of t will be A by Kv. And the same line, third one is acceleration coefficient, Ka, limit s tending to 0 s square G of s H of s. And in that case the error ka formula becomes A by Ka. Okay. Yeah. So the next thing is now fourth, fifth one. Any other formula? The type of the system. Some of the students in the revision class asked me this thing, right? So type, keep in your mind, type of control system comes from OLTF. So OLTF should be with you. Correct? And the second thing is order of the system. Let me talk about the type only. We'll finish up with type and then we'll go. Now OLTF is what? OLTF ka formula is, OLTF is, G into H, whatever is the forward transfer function multiplied by the feedback transfer function that is there. So in this, whatever number of poles are there at origin, that gives you type of the system. Number of poles at origin. Now means what? How you are going to get whatever is the value of this, what you are going to have? You are going to have some gain k, some zeros in the system, correct, which will be in the numerator. Some poles will be there, which definitely are in the denominator, poles, right? And you may have s raised to something over here. So might be nothing is there, s raised to 0 is there, so the type becomes 0. But if this j exists over here, s raised to something exists, j will decide the type of the system. Alright? On the same line, if you are talking about order of the system, then this order comes from CLTF. दोनों mix नहीं करना है. These two things are different. Now what is CLTF? CLTF is G upon 1 plus GH. Right, and whatever is the denominator of it is the characteristic equation. So I'll write characteristic equation is 1 plus G of S H of S equal to 0. So in the CLTF, whatever is the denominator, you equate it to 0, you will get the characteristic equation. And in the characteristic equation now, highest power of S will give you that order of the system. So highest will give you order of the system. ठीक है, okay, and we'll solve one numerical. So you'll come to know on which line you are going to move. Definitely it's very difficult to explain only one numerical. I mean, based on only one numerical we can say yes, this is the in this way you are going to solve, but it can be a sample with you. थोड़ा बहुत changes हैं in the numerical, definitely you'll be able to go for it. ठीक है, yeah. So I'm writing a numerical and I'll try to solve it. Yeah. So for a unity feedback system, OLTF is equal to K S plus 2 upon S square, sorry, S cube plus 7 square plus 12s determine number 1, type of the system, order of the system, third thing is error constants or error coefficients, both the things are same, that is KP, KB and KA. And fourth one is steady state error, ESS of T, steady state error for unit parabolic input. Okay, so these many things we are supposed to do. Okay, so first thing is we'll go for the type of the system. Okay, number 1 in OLTF. Now I can write the OLTF as K into bracket S plus 2 upon see, and in this type mostly the question will be based on these coefficients. Find out the coefficient and find out the error for that particular input that is given, right? Nothing else. Type of the system, only the transfer function will change and the type of the system will change. Based on that you will find yes, the coefficients will change and the error is going to change. So very well I can see I can take S common, so it is going to be S square s square plus 7s plus 12. So you can see that s raised to 2 here, s raised to j, k, some zeros, some poles, factors, definitely we can have factors for this, but separate s that you are having at origin, s raised to 2 is there, so j ka value is 2, so type 2 system. Okay, one thing is clear. Then the second thing is you are supposed to get the order. Now order ke liye you should know the characteristic equation, and very well you know that the characteristic equation is denominator of this 1 plus g h, and you know OLTF means what? G h h s, g of s, h of s, right? So that means what I can write, therefore I can write 1 upon k s plus 2 upon s square plus 7s plus 12 and equal to 0. तो क्रॉस मल्टीप्लाई किया तो यू आर गोइंग टू हैव s square plus 7s plus 12 plus k s plus 2. So definitely very easily understood that highest power is going to be 4. So we'll be able to write order is 4. Okay. Then the third thing is you're supposed to get Kp, Kv and Ka. So Kp ka formula you know, I've written it over here. Limit, I'll not put everything now, I'll just show you. S tending to 0 and g of s, h of s, which is your OLTF, which is given over here. That is K s plus 2 upon s square plus 7s plus 12. So very well clear, s tending to 0, this is tending to 0, will go in the numerator and will be infinite. Then for kv, limit s tending to 0, same thing, only it is getting multiplied by s now, so we have to multiply it by s k s plus 2 s square plus 7s plus 12. One s will get cancelled out, still one s is remaining in the denominator, ऊपर जाएगा, it is going to be infinite. Now for ka, limit s tending to 0, now it is s square k s plus 2 s square plus 7s plus 12. So this s square will get cancelled out. When you put s is equal to 0, everything is getting cancelled out and it will be k by 6, because this is 2k divided by 12, that is k by 6. Done. Now the fourth part is unit parabolic. Now r of s, in this case unit parabolic means 1 upon s cube. Now two ways are there to solve. I will solve by both the ways, right? You want to get ESS of t, this thing. So I'll put the value ESS of t is equal to limit s tending to 0, s, r of s is 1 upon s cube upon 1 plus gh का value is this k s plus 2 upon s square plus 7s plus 12. So whenever this thing will go in the numerator, this becomes s square. This thing will go in the numerator, this s square will also get cancelled out, and you are going to have limit s tending to 0, right? S square I have cancelled out, otherwise I'll write s square s square plus 7s plus 12 whole thing divided by, see, this is going over here, so it is going to be s square plus 7s plus 12 and plus k s plus 2. So this s square is getting cancelled out when you substitute s tending to 0. Ye gaya 12. This whole thing will go. This s will go. 12 divided by k2 or 2k. So it is going to be 6 by k. On the same line, if you want to go by the other way, ज़्यादा shortcut है, right? You know that you are talking about parabolic input. In that case, your ESS of t is a by ka. So I can write ESS of t is equal to a by ka, and we got k as k by 6. So, and a is 1 because it's unit parabolic. Coefficient in the numerator is 1. So it is going to be 1 upon k by 6. So it is going to be 6 by k. Okay. So in this way you can solve the numericals for this thing, steady state error. Next video will be for second order system. Thank you.